Hi, I'm
And
Anna.
I'm Mia, and this is our Chapter 2 review. One of the most hard and crucial concepts of Chapter 2 is the introduction of two-column proofs. A two-column proof is essentially a geometry roadmap. You want to get from point A to point B. Point A is called the given, where you start out. Point B is the statement you have to prove from other logical statements and the diagram given. These logical statements are theorems, postulates, and definitions. Postulates are the unquestioned truths of geometry. Theorems can be proved by these postulates. Please take a look at your copy of the Geometry Postulates, Theorems, Definitions, and Property sheet. These are all really important to solving various proofs that you may have to solve. We will be using some of them in the following examples. Here is a proof you might solve later on. This is the given, which is B is the midpoint of segment AC, D is the midpoint of segment CE, and segment AB is congruent to segment DE. What you need to prove is that AE equals 4AB. This over here is the diagram, which is a required and necessary part of any good two-column proof. By the way, the column on the left that is labeled statements are for the steps we are going to use to prove that AE equals 4AB in this case. The column on the right, or the reasons, are where we place the definitions, postulates, theorems, and properties depending on what we use to get to justify our statements. Now it's time to get started on this proof. Okay, so our first step on our two-column proof is to start off with a given. After all, how's one supposed to know how to prove something if you don't know where to start off? Let's take a look at what we have. Okay, so we have B is the midpoint of segment AC, D is the midpoint of segment CE. Wait, can the definition of midpoint help us here? Oh yeah, that AB equals BC and CD equals DE. That should be step 2, because that's definitely going to be helpful in proving that AE equals 4AB. Now that we have that down, we should take a look back at the other given we didn't use. Segment AB is congruent to segment DE. We can use another definition here. Due to the definition of congruent segments, that makes it AB equals DE. At this point, it's visually easy to see that A equals 4AB. Well, at least for me, that is. From here on out, you can tell it's going to be a mix of converting this figure into a doable algebra formula. So let's do step 4. What's the postulate that can easily convert this figure into a simple formula? Yeah, you got it, the segment addition postulate. Let's start with the obvious for step 4. Step 4 will be AC equals AB plus BC, and CE equals CD plus DE. For step 5, let's think a little bit bigger, so we can substitute later. So AE equals AC plus CE. So essentially, AE equals AB plus BC plus CD plus DE. That should be step 6 because of substitution. Therefore, because of substitution again, AE equals AB plus AB plus AB plus AB. That's step 7. Due to substitution for the last time, AE equals 4AB. Congrats, you did it! Our last proof of the video, yay! We have that angle 5 is congruent to angle 6, and we want to prove that angle 4 and angle 6 are supplementary. Remember what to start off with on this point? I know, it's just so hard to remember what I just said a couple seconds ago. It's crazy. So first we start off with a given, which is angle 5 is congruent to angle 6. I know it doesn't look like it on the diagram, but this is geometry and we prove things by logic, not by measuring. Anyways, let's see what we can salvage from this given. By definition of congruent angles, measures of angle 5 are congruent to angle 6. I see a substitution in our future. Anywho, let's pay some attention to angle 4. Well, due to the definition of linear pairs, angle 4 and angle 5 are supplementary, which of course means that measures of angle 4 and 5 equal 180 degrees, because of the definition of angles, which, means that by substitution, that measure of angle 4 plus measure of angle 6 equals 180. And now we're kind of going backwards, so by definition of angles, angles 4 and 6 are supplementary. Whew! You did it! And that's how you solve a proof. With two-column proofs, you basically follow these general steps, and with enough practice, you'll get the hang of it in no time. Remember, proofs are like a geometry roadmap. A proof is a logical math puzzle. A specific number of puzzle pieces are needed to solve the proof. No more, no less. Logic helps you determine how many puzzle pieces are needed, and logic itself is a subject within geometry. Some vocabulary is needed to better understand how to solve logic problems. These are specifically different types of reasoning used to come to a conclusion. Here is some vocab you have. Inductive reasoning is reasoning that uses a number of specific examples to arrive at a conclusion. All you need to remember is that inductive equals example. Deductive reasoning uses facts, rules, definitions, or properties to reach logical conclusions from given statements. Just remember that deductive equals one rule. Last, but certainly not least, is a conjecture. This is the official name of the concluding statement reached during inductive reasoning. That's some basic reasoning vocabulary for you. Next up is some truth table vocabulary that will help you solve the following problems. This is personally my most favorite bit of this entire chapter, and I am really excited to explain this. Anyways, a truth table is just a convenient method of organizing truth values of statements. These are compound statements that are two or more statements joined by the word and or. A compound statement using and is called a conjunction. A compound statement using or is called a disjunction.
This is the truth value, this is the negation, this is the compound statement, this is the hypothesis, and this is the conclusion.
Yay, our first truth table! For truth tables, you have to list all of the possibilities, like what I have shown. Next, we do the opposite of Q, as that is what it means to negate the conclusion in this case. Whenever you see the curvy sign like this, you do the opposite of what it's telling you to do. So that would be false, true, false, true. Next, we have to find the disjunction with the P and not Q. For disjunctions, we just need one true, so that would be true, true, false, true. Good job. Aw, man, this is our last truth table. My heart is aching. Anywho, remember we started off this truth table by listing all the possibilities all over again. You have to remember this pattern. Besides, it isn't that hard to remember. First, we negate P. So again, that's the opposite of P. So, false, false, true, true. Next up, we do a conjunction of not P and Q. With conjunctions, you need two P's for it to be true. So looking back, it will be false, false, true, false. And in this last one, we're going to negate the entire thing. So that'll be true, true, false, false. Hey, we ended up right where we started. What we've been proving are conditionals, or an if-then statement. P is the hypothesis and Q is the conclusion. Some other related conditionals include the converse, which is exchanging the P and Q. Another one is the inverse, which is found by negating the hypothesis and conclusion. The contrapositive is a mix of the inverse and the converse, where you switch P and Q and negate both. Here we have some basic forms of deductive reasoning. This one is called the law of detachment. Here, if the given is true, then the conclusion is true as well. This one states that if P then Q, and P is true, then Q is true. Second, the law of syllogism draws conclusions from two true conditional statements, when the conclusion of one statement is the hypothesis of the other. If P then Q, and if Q then R are true, then if P then R is a true statement. And lastly, and one of the most important laws to remember is modus tollens. This one isn't stated in the textbook, so it's best to keep this one fresh in your mind. This one says that if the conclusion is false, then the hypothesis is false. So if P then Q, and Q is false, then P is false. Thank you so much for listening to this video. We hope you had a fun time. This isn't The Last of Us, though. Next we're playing Candyland, in a perfect little geometry version. Ani worked really hard on the game. I always find playing board games so much fun, don't you? I had this little fascination with Candyland when I was little because I thought that I like all of the board because like all the board food figures on the board look so yummy. I wanted to be like Princess Lolly for the longest time ever. I mean, she's a princess of candy. But then Queen Frostine became my next idol because she's always looked so effortless and pretty and frosty and yum. Lord Licorice scared me though. I mean, who has a mustache like that? That sneering grin. Ew. Okay, I'm sorry for ranting. It's just that I really had a fun time making this video, and I really want to prolong this because this was just so darn fun. But now it's all over, and I only dropped the casual hints that I wasn't having fun because I want to be a cool, normal teenager. I give up. I like math. And I love truth tables. Okay. Sayonara. Adios. Farewell. Barkatu. Ayos. Desvinanja. Vel. Yasas. Salutes. I'm sorry, I don't know any of these languages. Okay, seriously, bye.